We continue the discussion on clustering. As we had mentioned in the previous lecture that we want to group points into homogeneous groups, and the homogeneity is measured by the ratio of the average distance between the points which lie in the same cluster to the points which lie in different clusters, the scatter coefficient. And we find we discussed that there are two ways of doing this. One is partitional, where we try out all possible groupings of the point and select the one having the best, and the other is hierarchical, where we either split the points starting with all points in the same cluster and then splitting them based on some criteria, or we do the reverse bottom up, that is initially consider every point to be a separate cluster and then group them one by one. So, and we found we saw that, so this is what we had already discussed. We need some kind of the basic assumption is we need some kind of similarity before we start the clustering. So, that can be distance or anything. So, we first discuss the methodology of this kind of hierarchical clustering, where we merge them and get different clusters. And there are two kinds, as I have told: agglomerative, which is bottom up, and divisive, which is top down. And we have also shown that what we construct basically is a tree like structure explained here, which we called a dendogram. Before I go into the method, so one of the I want to just quickly mention some of the properties. We will discuss these algorithms. Before we discuss them, we tell that some of the properties we desire of the clustering algorithms is that it should be fast, both in time and space. It should be fast, it should be deal with not just numerical, but nominal, ordinal attributes also. It should be able to deal with noise and outliers. It should be independent of the order of the input records, and if necessary you should specify certain constraints and finally interpret. So, these are some characteristics we need. So, what I will do is that I will now explain the hierarchical clustering starting with the bottom up, that is the agglomerative approach. So, let me explain you with the help of points, as I have always done. So, your points are say two dimensional points given say like this. These are some points. Note that we do not have any class information here, we only have the similarity between some distance between the points, and you have to find the natural clusters, the natural groupings. So, I explain hierarchical agglomerative clustering. And I will tell you way of constructing the cluster tree as I had shown before, or the also known as the dendogram. Let me explain. So, suppose I have n points p1, p2 up to pn, n two dimensional point. It may be in higher dimension also. Actually, there need not be points like this. All I need is a distance matrix between the points. So, if there are n points, all I will need for this is a kind of distance matrix, which is a for n points a n by n matrix, which tells you every entry tells you the distance between point I and point j. So, the distance between p1 and p2 will be this. It tells you. So, every distance matrix is dij, the distance between I and j point. So, all I need for hierarchy, I need not know their coordinate values also, all I need is their pairwise distances, distance between every pair of points. So, let me explain. I am writing down again, so that you can check the note. Okay. So, the idea is like this. So, in the leaf of the dendrogram, you consider all the points as all the points. So, P 1, P 2 up to P n. Assume every point is a separate cluster. So, every point is a separate cluster. Of course, they will be singleton clusters because there will be only one element per cluster, but we start with that. Every point is a separate cluster. So, there are n clusters if there are n points to be clustered. Now, what you do, check the pair of points which have the least distance between them. So, you consider pair of points having least distance between them. Suppose, I am just explaining, P 1, P 2 are the closest pair of points. So, what I do, earlier there are n clusters, P 1, P 2, P n, every point a cluster, every point a cluster. Now, if P 1, P 2 are closest, they get merged, these two clusters get merged, these two small clusters get merged to a slightly larger cluster containing 2 points. Earlier a cluster had 1 point, now the cluster has 2 points. Other points are single point clusters. So, in the next level of this tree, I have n minus 1 clusters. In the next level, I have n minus 1 clusters, because two points got, 2 clusters got merged. Okay. So, now I can to further build the tree, I can visualize it like this. So, this is a 2 point cluster and these are single point clusters, but they are clusters. Now, I will merge 2 clusters which are closest, merge 2 clusters. I have not yet defined what is closest. I have defined 2 points, how they are closest I have defined by their distance, but how 2 clusters are closest I have not yet defined, I will define soon. Okay. So, in the next level, merge 2 clusters that are closest. I am not yet told what is closest means. Okay, but suppose I have some measure what is closest. So, what I will do, I will merge. So, it is possible that these 2 clusters are closest, or these 2 single clusters are closest, or this and this is closest, whatever, whichever is closest. Let us say this 2 is closest. I merge it. So, now what happens? Now, I have n minus 2 clusters, one cluster 2 point, another cluster 2 point, and rest single point clusters. Okay. So, in the next level I have, so here I had n, here I had n minus 2 clusters. Now, repeat this again, merge 2 clusters among this after this step. Merge 2 clusters that are closest. So, what may happen? Maybe now this cluster and this cluster is closest. So, they get merged into a 3 point cluster. Okay. So, 3 point cluster. So, you see I am gradually building the tree and repeat this. Clusters that are closest. Just go on repeating this. Just take 2 clusters that are closest. Let us say now these 2 get merged, maybe after one more step these 2 get merged, then maybe after one more step these 2 get merged, and maybe after one more step these 2 get merged. Okay. So, this is repeated till all the points belong to a single cluster. The root. Okay. So, this tree is the dendogram. So, I repeat once again what I did. Initially, if I had to cluster n points, each and every point is a cluster, and then I go on merging 2 clusters which are closest again. I have not yet told again what is closest. I keep on merging the closest cluster. 2 clusters which are closest, they merge together from one cluster. I keep on doing this. I keep on doing this till everything get merged to a single cluster. Okay, and I get the dendogram tree. Okay. So, now you will say you have just got a tree. So, how do I get my groups? How do I get, suppose I want to divide the point into 3 clusters. How do I get 3 clusters? So, what I do, I look at the level of the tree where there are 3 branches. So, this level there are 3 branches. I cut the tree there, and each of the branch form a cluster. So, now there are 3 clusters, this 2 one cluster, this 4 one cluster, this 2 one cluster. Okay. So, I cut the dendogram at k minus 1 height, k minus 1 if I had to get k cluster, right. Okay. So, so this is agglomerative bottom up. The reverse of this is divisive. Reverse of this is divisive. So, what happens there? There I initially all the n points form one cluster P 1 to P n, and then they are divided into 2 clusters based on 2 sets of points which are farthest. Then they are further subdivided till they are farthest, and go on doing this till every point is a separate cluster. Okay, is a separate cluster. So, same dendogram, but now constructed the other way around. And again, if you want k clusters, you cut at the k minus 1 height. Okay. So, this is clear. So, both hierarchical, divisive and agglomerative, this is clear. You basically construct a tree and then cut the tree. And how do you construct the tree? In bottom up, you merge the initially every point is a cluster, then merge the closest ones, and divisive everything is a single cluster, and you divide the farthest one. Okay. So, now I will define distance between 2 because I have told you that you have to merge the closest clusters. So, how do you measure closeness between two clusters? Okay. How do you measure the closeness between two clusters? So, let me check here. And say this is another. So, I have say two cluster C1 and C2. So, what is a measure of distance between C1 and C2? Okay. There are three options. One is the average distance. You take the centroid of both the clusters and distance between them is the distance between two clusters. Not the distance between 2 points I have previously defined, either Euclidean or Manhattan or something I have defined. Using the distance between 2 points, I am defining distance between two clusters. Okay, is that one possibility, average distance, mean distance, minimum distance. So, you define distance between two cluster at the distance between the closest 2 points in the cluster. Closest 2 points in the cluster. Closest 2 points between the clusters. Similarly, you can take maximum distance. Where the distance is the distance between farthest 2 points in the cluster. So, points in the cluster. Okay. So, three different ways you can measure it. Depending on which way you measure, you have a different. So you remember, so what I will do, you remember the hierarchical agglomerative or divisive, I was telling that merge two clusters having closest, which are closest. So, now closest will be measured in terms of either this or this or this. Okay. That is how closest will be measured. Okay. So, depending on which of these three you use, you have three names for these hierarchical algorithms. If you use the minimum, if you use the average distance, you call it a average linkage clustering. Remember the name, average linkage clustering. If you have the minimum distance as the closeness, you have the single linkage clustering, one of the most popular algorithms, single linkage clustering. if you have the maximum distance, you call it a complete linkage clustering. Complete linkage clustering. Okay. Single linkage, complete linkage, average linkage. The method is same dendrogram, but closeness of two clusters is differently defined. So, this single linkage clustering also has a graph theoretic implication. See how I have told you merge two clusters having closest same point. Closest merge two clusters having closest nearest neighbors, closest 2 points, that is the single linkage. Okay. So, this Dendogram construction, note that single linkage means the closeness is the distance between the closest pair of points. Construction actually produces a minimal spanning tree. I will explain what it is. You might have, those who have done a graph theory course might have heard this term. Okay. So, what you do is the following: take every point, this is one, this is one, so two groups of point. You make a tree, that means you connect a tree like structure. So, 2 points, there is only one path between 2 points. Okay. Similarly, here. Only one path between 2 points. Okay. So, it is a tree, there is no cycle basically, there is a tree and it is a spanning tree. That means, every point is a node, tree. It is a spanning tree. That means, every node is, there is a path, no node is disconnected. And if we take these edge weights to be the distance between these 2 points, the total cost of the tree is the sum of all these edges. So, edge weights, and among all possible tree, this is the minimum. So, that is why it is called a MST, minimal spanning tree. So, actually the Dendogram construction is same as the Prim's algorithm of minimal spanning tree construction, those you know. So, what you do in single linkage clustering? Take the points P n, construct a MST. Now, to get k clusters, cut the heaviest having the highest weight, so if you want to get 2 cluster, cut the heaviest weight. you want to get 3 cluster, cut 2 heaviest weights, and that will partition the points. In since it is a tree, it will partition the point into 2 groups. Those are your clusters. Okay. What are the advantages of single and complete linkage clustering? See, if you have arbitrary separate clusters, the algorithm will still find them. Non-convex, that means convex means like this, closed, it is non-convex. Some disadvantages. If you have a noise point, then this algorithm fails. So, sensitive to noise. So, imagine like this, it will be completely wrong. Noise, time consuming, slow. These are the disadvantages. Okay. So, this covers my discussion on these 2 algorithms. In the next lecture, we will discuss the partitional clustering algorithms, okay, which will is like as I have mentioned, it evaluates the partitions. Thank you.